Am I audible to all of you? Guys, am I audible? Alright. So, good morning, all of you. Today is lecture number 5 on the subject of science and environment. Oh, sorry, science and technology for the subject of nuclear technology within the topic of science. So, guys, when you talk about nuclear energy, we have so far completed the general science part of nuclear technology. We have finished what is strong nuclear, weak nuclear force, what is radioactivity, what is the application of, I think, application of nuclear energy we were discussing in the last class. We'll try to complete that today. We have discussed some of the applications, although we have seen the application of radioactivity. Then we have learned what is controlled, uncontrolled nuclear reactions. How do we harness nuclear energy in the form of nuclear fission, nuclear fusion? What is the trigger condition for both nuclear fission, nuclear fusion? And then we have also seen how India aspires to become a nuclear powered nation or civil nuclear powered nation through its 3-stage program, right? We have finished up till here. Any questions if you have, please ask. And mind my word, students, today is the 5th class. So this was the class that was supposed to be open for all the students, right? Everyone could have joined up till lecture number 5. Now after this, we will have classes only for the students who have enrolled at PMF. So you guys understand that this is the last lecture that is open to everyone. And in fact, I would also recommend, if you guys have been satisfied so far, if you think that we have been able to add a little more value to your understandings, please do share with all your friends, all your all your classmates, if they would be interested to join this course, right? I to the best of my consideration, to the best of my knowledge, what we are delivering here is probably the best in the country, right? There are very few people that I know who are really adding a lot of value in terms of content and in terms of teaching, and fortunately all of them are right now associated with PMF. So you guys can take the decision here. All right. Now, and when it comes to notes, there were some students who had some concern regarding the notes, regarding the class notes and study material. See, first of all, for science, the book was supposed to be launched. It is supposed to be launched in the month of November, the full book. But for the students who have already enrolled, chapter wise, they would be sharing PDFs. So chapter wise PDFs you may receive. You may not receive the full book, but you may get the chapter wise PDFs for all the things. So you can start reading from that way, from that source. And secondly, one of the students have also made a request regarding lecture wise notes. Now see, although I'm sharing the annotations, I'm sharing the PPTs with all the annotations in it. You can access those PPTs. Those PPTs will have everything which I would have written in the class, right? And some students are finding it difficult to write and make notes alongside. I would recommend that, because lecture wise I have not made any separate notes, because you have to understand that sometimes some new updates can happen, and I may cover up those updates also. I may talk about those updates which may not be the part of my handwritten notes if I write them once. But there are still some other handouts that I've made, which are general science related handouts. Those handouts I'm going to share for every chapter. They are there. Okay, so alongside with the chapters of PMF, you will also have my own handouts that I'm going to share with you. All right. So guys, anything to ask? Any questions from the previous class? If you have, please ask. Anything to ask? Any questions from the previous class? So we have finished up till here. All these topics are covered. Yeah. So I think we were discussing application of nuclear energy, where I told you about food irradiation technology, which has already been approved by FCI and FSSAI. Then I also told you about the controlled gamma ray mutation technique, which is a way of silencing some of those genes which are undesirable, right? So it's basically using gamma rays to silence the genes. There is another method of gene silencing which I'm going to talk about when I'll discuss biotechnology. That's a different approach there. Okay, so guys, let us continue with this. I'm hoping to finish the entire technology part today itself. So let us talk about the next application here, that is healthcare. Let's talk about healthcare application of nuclear energy. and this is probably the application which all of you might already know, healthcare. See, first of all, there are lot of areas, there are a lot of applications when you talk about nuclear technology and its impact on health. There are a lot of areas. You guys are already aware of things like, you know, cancer treatment, cancer care. Whenever anyone has got his bone fractured, we go for an X-ray scan, right? CT scan is also nothing but a type of X-ray scan only, which has multiple X-ray cameras. So likewise, all these are application of nuclear medicine only. But there is one specific application I would like to mention, because that can have higher relevance in the exam, and that application is for cancer treatment, nuclear application or nuclear medicines for cancer care. Guys, if I ask you what do we understand by cancer, what is the meaning of cancer, guys? If I ask you this question, what do we understand by cancer? I believe most of you would say cancer is nothing but uncontrolled multiplication of cells, right? That is true, by the way. Cancer is uncontrolled multiplication of infected cells. If suppose any cell of our body has got infected, and unfortunately our immune system has stopped recognizing it as an infection, and this infected cell starts multiplying, then those infected cells multiplying uncontrollably, we call them cancerous cells, right? So cancer is uncontrolled multiplication of infected cells. Now let me tell you one thing, that we still do not know a concrete reason. We still do not have a very concrete reason of why cancer occurs. It is quite a surprise that even so much of innovation, so much of development in medical science, we are still not in a position to actually predict the right reason for cancer. People with some of the most healthy lifestyle can also develop cancer. People with poor genetics can also develop cancer. People with with an unhealthy lifestyle can also develop cancer. Today we keep cancer as a non-communicable lifestyle borne disease. It is mostly developed due to unhealthy lifestyle. So what I'm saying is that cancer happens to be a very severe disease, and it is not known to us what exactly are the reasons. There could be multiple reasons for cancer. In fact, guys, distortion of the circadian rhythm can also cause cancer. Do you understand what is a circadian rhythm? Circadian rhythm is our natural body clock. Circadian rhythm, right? It is our natural body clock. Circadian rhythm, it is a natural body clock. Like you must have noticed that if you always have a habit of eating your breakfast, let's suppose at 8 a.m. in the morning, then automatically around 8 a.m. you will start feeling hungry. If you have a habit of sleeping at 11 p.m. at night, at 11 p.m. you will automatically start feeling sleepy, right? Your body adapts to a certain natural biological clock. It's called circadian rhythm. If somebody has a high distortion in the circadian rhythm, even that can also be a reason for cancer. So cancer, it's very difficult to predict what could be the exact reason, right? But when it comes to cancer treatment, nuclear technology holds a lot of key advantages, right? Now, can anyone answer which is the most common type of cancer in India? Can anyone tell me the most common type of cancer in India? Anyone? Which is the most common kind of cancer in India? Alright, I'll answer that. So when it comes to females, in females, the most common type of cancer is breast cancer. And in case of males, it is mouth cancer. Mouth cancer happens to be the most common type of cancer in males, and breast cancer in females. Second most common cancer in females is cervix cancer, which is also the uterus cancer or cervix cancer, right? So this is what is the maximum cases of cancer in India: breast cancer in females and mouth cancer in males. Now guys, when you talk about cancer therapies, when you talk about cancer treatment, there are usually three types of treatments that we have. The treatment number one, the most famous, chemotherapy or chemical therapy. In chemical therapy, what happens? The doctor will call you for an appointment. He will insert a cannula into the veins, and then they will push a combination of lot of medicines into the blood. When they will push a combination lot of medicines, the blood is going to carry all those medicines to all parts of the body. the blood would carry those medicines to every part of the body, right? Now let's suppose if somebody has got liver cancer, the medicine will take, the blood will take the medicine to every organ, not just the liver. In this case, in the case of chemical therapy, because all the other organs are exposed to the medicine, the dosage that is required to treat cancer is usually kept higher, because the amount of medicine going to the liver is less, because you are putting the medicine through blood, and blood will take it to every cell of the body, not just every organ, every cell of the body. So normally we keep a high dosage, a high concentrated dose, and because of that high concentrated dose, there could be a lot of side effects also of the same treatment. You guys must have heard people lose their hairs, people develop some kind of body ache, yeah, right, their immune system becomes very weak. All these kind of things are possible side effects of chemotherapy, because it is not just the cancer cells, but every other cell of your body gets exposed. And doctors, what they do, once the chemotherapy starts, then they go for frequent scanning, and they will check if the chemotherapy is working, if the cancer tumor is shrinking or not. If the cancer tumor starts shrinking, that means the chemotherapy is working and the patient may be able to recover. In 95% of the cases where people are diagnosed a little early, in early stage cancer, they can easily be prevented. They can easily be treated through chemotherapy, right? But this is the first therapy, but it brings in, or it comes with lot of side effects. The second type of therapy, this is basically the therapy which involves surgeries. Now you know what, or the second type of therapy is basically, I'll take example of nuclear radiation. That is the nuclear medicine or nuclear radiation, or we can call it gamma ray therapy. In this therapy, let's suppose somebody has got a cancer tumor somewhere here. They will go through a PET scan, they will go through various scanning to find out where exactly the cancer tumor is, and then they will use some gamma radiation to bombard onto the cancer cells, and those cancer cells would be killed through the gamma rays. Now the advantage of this therapy is that this therapy only exposes the cancer tumor cells to the gamma rays. Of course, some little bit of side effects may be here, because sometimes some healthy cells around the cancer cells may also get affected, but the amount of side effects is much lower. And another advantage is that this type of therapy can be applied for different ages except young ones. Except young ones, it can be applied for multiple age groups. And one more thing is, in India also we have got an institution, we have got a technology based on gamma ray cancer treatment. It is called Cyber Knife. If you go to AIIMS Delhi, you will find a separate laboratory, you will find a separate building for Cyber Knife, and it's a very famous technique now for gamma ray based cancer treatment. Now this is supposed to be better than chemotherapy because it has less side effects, and the chances of survival is also quite high. It can even work in later stages of cancer as well, right? But guys, when it comes to the most common types of cancers in India, when it comes to the cancer of breast cancer and mouth cancer, unfortunately, this nuclear medicine or gamma ray technique or cyber knife technique is not there. We do not have the nuclear medicine technology available for breast cancer, neither for mouth cancer. Now, what type of therapy is normally adopted for this type of cancer? So here doctors normally go for the third therapy, that is surgery. Surgically removing the cancer. Now surgically removing the cancer means cutting a part of the breast and removing it out. Cutting the part of the jaw, removing that jaw out. You guys can simply understand how badly it would affect the self-confidence of the person if he has lost a part of his jaw. And guys, it is also difficult for the family as also to accommodate, because the entire lifestyle changes, right? Thankfully, now we have got an alternative for at least breast cancer treatment in the case of cancer therapy for nuclear or through nuclear energy. Please write down something called cyclotron. The spelling would have been same. Write down cyclotron, and under cyclotron write down cyclone 30. Please write down cyclone 30 and cyclotron. First, let me tell you what exactly is a cyclotron. Write down, a cyclotron is a particle accelerator. A cyclotron is a particle accelerator. A cyclotron is a particle accelerator that is used. It's a particle accelerator that is used for a cyclotron is a particle accelerator that is used for creating artificial radioactive isotopes. It's a particle accelerator that is used for creating artificial radioactive isotopes. It is a particle accelerator that is used for creating artificial radioactive isotopes. Artificial radioactive isotopes. Okay, so particle accelerator used for creating artificial radioactive isotopes. So remember guys, with this particular term cyclotron, it should be clear in your mind that it is possible for us to create artificial radioactive isotopes with a device known as cyclotron. Now what is Cyclone 30? Cyclone 30 is the largest cyclotron in India. It is the largest cyclotron of India. It is located at Kolkata, right? Largest cyclotron of India, and it is located at Kolkata. And guys, this Cyclone 30 is a cyclotron which is capable of producing artificial radioactive isotope, that is germanium. Artificial radioactive isotope. Just 1 second, please. So it's a artificial radioactive isotope capable of producing germanium 68. Germanium 68. And guys, this germanium 68 is a radioactive isotope used for diagnosis and treatment of breast cancer. Diagnosis and treatment of breast cancer. So for diagnosis and treatment of breast cancer, it is now possible for us to use, nuclear medicine or radiation therapy, right? So this radiation therapy is now available for breast cancer in India. And guys, you can understand with radiation therapy, it is considered to be non-invasive, guys. Non-invasive means that we are not putting anything inside the body. The radiations are exposed from outside. But yes, of course, in this therapy also there is some kind of injections that are often put to trace the cancer cells. Okay, so I hope all of you guys are able to get it. This is what is known as cyclotron. Remember Cyclone 30. In the handout that I'm going to share on India's nuclear power plants, today I'm going to share that handout. It will have Cyclone 30 and all those things there listed. I hope all of you guys are able to get it. This is what we have under healthcare. Remember, when it comes to nuclear radiation and healthcare, there are many more other applications also. There are many other applications as well, but being limited to what is important, Cyclone 30 is more relevant in today's context. Okay. Now guys, the next topic is water safety. What is the importance of nuclear energy in water safety? So guys, just like we have been able to decontaminate food, we have also been able to decontaminate water. And there are not just one but many innovations that has come in the area of water safety. One innovation is Nisargun. Akruti. These are basically solutions for wastewater management using nuclear energy. So as nuclear energy can help in decontaminating the food, see, when it comes to water safety, there are two types of water. Ecology students may be able to recall. There are two types of wastewater. One is called black water and the other one is called grey water. Black water and grey water. Grey water is basically the water that comes from, your kitchen, the water that comes from kitchen, the water that comes from bathroom, right? Those bathing water and all these things, that is called grey water. Now grey water is supposed to have less contaminations, and grey water is expected to be easily recycled, easily reused. So we can use the grey water for agriculture purposes. It is not considered to be a problem. Grey water, the water that is discharged from kitchens and bathroom. But the other type of water is called black water. Black water is basically the sewage water that goes from toilets, right? and the water that also goes from medical institutions such, that is called black water. Black water is the one which has high amount of dangerous microorganisms and infectious organisms, right? So you must have heard that during the time of Mahakumbh there was some news regarding some bacillus coliform, right? It was basically a bacteria that is found in the fecal matter. So fecal coliform, bacillus coliform is basically the name. So it's a kind of fecal bacteria found in the fecal matter, which is a part of the black water. Now black water cannot be discharged directly into the nature. It should undergo a series of treatments, so that the bacterial concentration is minimized and it is not going to be harming the natural ecosystem. Now when it comes to black water treatment, that is where we require sewage treatment plant, and for factories we have ETPs, effluent treatment plants and such. So Bark has developed Nisarguna and Akruti as techniques that can improve the decontamination of black water. I hope you get it right. So for black water treatment, Nisarguna and Akriti could be good techniques for decontaminating the black water by using radioactive radiations. I hope all of you guys are able to understand. So these are all the applications of nuclear technology. Now there is one particular term that is listed here. It is called astrobiology. Now what exactly is astrobiology? I have not discussed astrobiology in this PPT, but I'll just tell you verbally what exactly this means. When we reach to the subject of space technology, that is our next chapter, in the subject of space tech, I'll talk about astrobiology in more detail. So what is astrobiology? Astrobiology basically means the study of living organisms. Like we know biology is the study of living organisms. Study of living organisms and the impact, it is the study of living organisms. How are they affected by space weather conditions? I'll explain this part. Guys, when you talk about the subject of physics, physics is the mother of science. Physics is the mother of all science. Every science is based on the subject of physics. So physics is the foundation for all the science, and that's the reason you can understand why I'm going to start with physics, right? Why I've started with physics actually. So physics is the mother of all science. So basically physics defines the laws how nature works, right? So physics helps in defining the nature laws. And based on these laws, we have the subject of chemistry, we have the subject of biology defined. So chemistry studies the chemical nature of the things, and biology studies living organism, life forms. Now unfortunately we have not discovered any life form outside the earth, right? We have not yet discovered any life form outside earth, although physics remains universal. The way how physics works here, it will be working even on Mars, on Jupiter, on any other planet, it will be working in the same way. Chemistry also works nearly in the same way from if you go outside earth. But because biology is the study of life, living organisms, and we have not discovered any living organism outside earth right now, so it is obvious that biology as a discipline is limited to planet earth right now. But as we know that humans have been aspiring to go in space, already we know humans have gone into space. They are there in International Space Station. You must have heard, very recently Sunita Williams, an Indian origin astronaut, she spent more than 8 months in space, right? So there are people who are going into space now. You may be knowing that we also have aspirations. India also have aspirations of sending Gaganyaan by the next year 2026. We also have aspirations of sending humans to moon by 2040. So when we are going to send people outside earth, earth has been the planet which has supported life so far. But when we start putting people outside earth, don't you think the impact of all those space activities, sun produces so much of space radiation, so much of gamma rays, x-rays, and so other harmful UV rays also. There are so much of radiation, so much of changes of gravity, changes of impact of gravity on the body. All these things changes in space. So how are all these factors going to affect living organisms is what we study in astrobiology. So astrobiology is basically a combination of physics and biology, and they study the impact of space conditions on a living organism, on a living cell, right? So you must be knowing that India also in this PSLV C60 mission, we have successfully germinated plant seeds in space, right? Even ISRO even released the video of that particular successful germination. We have been able to successfully germinate plant seeds. So that is a clear domain of astrobiological studies. So you can't expect to grow these seeds without an assistance of a biologist, a person who understands botany, zoology, and then understand the physics of space, and then we can design systems through which we can grow plants in space. That is called astrobiological research. Now, typically astrobiological research is a part of space technology and biotechnology, but I have put it in nuclear energy because as we know that space is full of radiations, right? Especially ionizing radiations of X-rays and gamma rays. It is important to replicate the models on Earth, and when we replicate the astrobiological models on Earth, we often use nuclear radiations because we do not have X-rays and gamma rays reaching Earth, right? So nuclear energy have some little application in the area of astrobiology. But don't worry guys, we will talk about astrobiology in detail when we study space tech. It is just I have mentioned the word here so that you understand the word, and you understand that in order to make models for astrobiological research in India or on Earth, we have to rely on nuclear isotopes to replicate the same kind of environment that is there in space. Got it all of you? This is what we have under the various applications of nuclear technology. Please write down yes in the chat one last time so that I would know that you have been able to understand application of nuclear energy or nuclear technology. All right, perfect, very good. So now this completes our topic of application of nuclear technology. Now after these applications, the next topic of our discussion, it is again going back to the 3 stages of India's nuclear energy development program. So guys, we'll look at the nuclear energy development program again, but this time we'll understand the concepts and the meaning of the terms of the nuclear energy program. But guys, before I start with this, I want you to please write down these 4 terms. Please write down the 4 terminologies: fissile fuel, fertile fuel, enrichment, and critical mass. Please write down the 4 terminologies, right? These 4 terminologies are very important to understand the next part of nuclear energy. And once I'm done with this, I will only have to discuss the working of a nuclear power plant, which will also be completing today only. So this will complete the entire technology part of nuclear energy, and then after that whatever would be left, it would be simply related to the polity part of nuclear energy, where we'll talk about the various laws regarding nuclear energy, and we'll also discuss the international relation part of nuclear energy like NPT, CTBT, and all those things. Okay, so guys, the first term that I would like to mention is critical mass. What exactly is critical mass? So students, you remember that uranium 235, this is bombarded with a high speed neutron, and the uranium splits into krypton, barium, plus 3 more neutrons, right, plus energy, right? This is how it happens. All of you remember, right? This is the reaction of nuclear fission. But guys, the question is, can nuclear fission happen in all conditions, or does it really need some minimum amount of uranium? Like if I have a nuclear reactor and suppose I put only 5 uranium nuclei and I bombard the neutron into uranium, is it possible that 5 nuclei of uranium are enough to start a chain reaction, like one will hit the other one and then the other one, then the other one? No. In order to support a nuclear chain reaction, in order to have a nuclear chain reaction, there is a minimum amount of nuclear fuel that has to be used. A minimum amount of nuclear fuel. See, you have to understand that when you are trying to bombard, you are bombarding neutrons, which is itself a particle inside an atom, very small, nanometer size, in fact smaller than nanometers, and you are hitting this particular neutron into a nucleus, which is also of nanometer scale. It is very difficult to aim correctly, at such a small dimension, at such a small size. So guys, what is critical mass? Critical mass is, you can please write down, it is the minimum amount, or you can say minimum mass of a nuclear isotope required. It is the minimum mass of a nuclear isotope needed it's a minimum mass of a nuclear isotope needed for a nuclear chain reaction. So in order to have a proper nuclear chain reaction, whatever minimum mass that you need, we call this as, so whatever minimum mass is required, we call this critical mass. So critical mass is the minimum amount or minimum mass of a nuclear fuel required for a nuclear chain reaction. So guys, here itself I'll quickly answer. When it comes to uranium, the minimum amount of uranium that is needed for a nuclear chain reaction is 47 kgs. 47 kgs is the critical mass for uranium. That means you at least have to put 47 kilograms of uranium in a nuclear isotope, in a nuclear reactor. Only then you can expect a nuclear chain reaction to happen. If you are keeping 46 kilogram, no reaction is going to happen, right? At least 47 kgs of uranium is required. But guys, you can also write down 47 kgs of natural uranium is required. Natural uranium is 47 kgs, right? Because that is the name of the fuel in stage 1. If you guys can recall, the fuel in stage 1 is natural uranium. So for natural uranium, the minimum fuel that is needed is 47 kgs. The second one is plutonium. In stage 2, what is the fuel required? Plutonium. For plutonium, it is 10 to 14 kgs. And also for thorium, stage 3, it is again 10 to 14 kgs. For plutonium and thorium, the minimum mass that is required is 10 to 14 kgs. For uranium, natural uranium, it is 47 kilograms. What do you understand by this, guys? When you look at this 10 to 14 kgs, what do you really understand? When you look at this 10 to 14 kgs, what we understand here is, that means at least 10 to 14 kilograms of plutonium or thorium is needed if you want to have a nuclear chain reaction. And when you compare it with natural uranium, you require at least 47 kgs. Guys, don't you think this clearly shows that thorium may be a better fuel than uranium now? Because if uranium is required by up to 47 kilograms, that means the moment the value gets lowered by 47 kgs, the reaction is likely to stop. And all that uranium that you have will eventually become waste. Whereas in the case of thorium, 10 to 14 kilograms is the minimum amount that is required. That means the moment the value of the fuel will get reduced by 14 kgs, only then it will become waste. So don't you think thorium is likely to produce less waste compared to uranium in longer term? Please write down yes in the chat if you guys are able to get it. Are you able to understand that thorium is better in terms of waste because it produces less waste compared to uranium? So guys, if UPSC asks you question that what are the advantages of thorium over uranium and why investing in thorium based program is always better, you guys can understand thorium is better than uranium, especially in the context of waste production. It produces less waste compared to uranium. I hope all of you guys are able to understand. You should write down this point here. So this is known as critical mass. Okay, I hope all of you have understood the word critical mass. It is the minimum amount of fuel required for a nuclear chain reaction. Critical mass. Now guys, let's start with the other three terms: fissile fuel, fertile fuel, and the meaning of the word enrichment. Fissile and fertile will finish it here. Enrichment will again go back to the next slide. So guys, first term is fissile fuel. The first terminology here is fissile fuel. Now what is the meaning of fissile fuel? Please write it down. Fissile fuel are those nuclear isotopes. Fissile fuels are those nuclear isotopes. Fissile fuels are those nuclear isotopes. Fissile fuels are those nuclear isotopes. Those nuclear isotopes that are capable of undergoing a nuclear chain reaction. Those nuclear isotopes that are capable of undergoing a nuclear chain reaction. Fissile fuels. So fissile fuels are those nuclear isotopes which are capable of undergoing a nuclear chain reaction. We call them fissile fuels, right? Nuclear chain reactions. We call them fissile fuels, guys. So those fuels which are capable of undergoing a nuclear chain reaction, we call them fissile fuels. That means if you bombard a neutron in this particular fissile fuel, the fissile fuel will break and produce additional neutrons which can further hit the nucleus, and the nuclear chain reaction will keep on going. I hope all of you understand. These are called fissile fuels. Now guys, let's look at stage 1. What is the name of the fuel in stage 1? Natural uranium. Natural uranium is the fuel in stage 1, and keep concentrating here, guys. So you may ask now, what exactly is the meaning of natural uranium, and why have we written only natural uranium? Why not uranium? So guys, when you look at uranium, we all know that uranium has atomic number 92. 92 is the atomic number of uranium. You all know this is the heaviest naturally occurring element. Atomic number 92. And guys, uranium has a total of 6 isotopes. There are 6 isotopes in uranium, right? There are 6 different types of isotopes for uranium. Isotopes, you remember, same atomic number, different mass number. So uranium 92 is the atomic number. But when you talk about their isotopes, one isotope is uranium 238. Another isotope is uranium 235. Another isotope is uranium 233. Another one 234, 232 and 236. These are the 6 isotopes of uranium. These are the 6 isotopes of uranium that we have identified, that we have discovered so far. But guys, why have I written 2 isotopes on the top and 4 isotopes at the bottom? The reason is, when you talk about naturally occurring isotopes of uranium, these 2 are naturally occurring isotopes. So natural uranium is actually a combination of uranium 238 plus uranium 235. Natural uranium is actually a combination of 238 plus 235. So natural uranium is not a single isotope of uranium, it's a combination of 238 and 235. And guys, between 238 and 235, it is uranium 235 which happens to be fissile. Uranium 235. So naturally there are 2 isotopes of uranium, 235 and 238 found on Earth. They are naturally isotopes of uranium, and of course if these 2 are natural, then these 4 are artificially synthesized. They are artificially synthesized again through cyclotrons, if you guys can recall, right? They are artificially produced. And natural isotopes only 238 and 235, naturally occurring isotopes. And guys, what is a fissile fuel? A fissile fuel are those nuclear isotopes which are capable of undergoing a nuclear chain reaction. So between the two, uranium 238 and 235, which one is fissile? 235. 235 is fissile. So remember, in natural uranium, 235 happens to be a fissile isotope of uranium. Got it, all of you? But guys, we have one more fissile isotope of uranium, and that is uranium 233. Although it is artificially produced, but uranium has one more isotope, uranium 233, which is also fissile. Isotope. Tell me yes in the chat if you guys are able to visualize. So what is a fissile fuel? A fissile fuel is one which is, when you bombard neutron into a fissile fuel once, the fissile fuel neutron breaks the nucleus breaks into more neutrons, and these more neutrons are also capable of hitting the nucleus of uranium 235, and the chain reaction will go on. Now guys, you can ask a question here. That if 235 and 233 are fissile, that means here you have to simply trigger the reaction. You trigger the reaction will start, neutron will hit the first nucleus, and then the reaction becomes chain reaction automatically, right? This is what is the condition of fissile fuel, that you only have to trigger the reaction and the reaction becomes self-sustaining chain reaction. But what about other isotopes of uranium? Is uranium 238 not capable of undergoing chain reaction? So let me tell you guys, uranium 238, it can undergo nuclear fission. If you bombard a high speed neutron into uranium 238 will also break. But when it produces neutrons in the reaction, as it produces neutrons, those neutrons will not have enough energy that they can hit the next nucleus and perform the same reaction. Are you able to understand? So why only uranium 235 and 238 are fissile fuels? Because here the energy of the neutron is maintained enough that every subsequent reaction will induce or will trigger the next nuclear fission reaction because of the high speed neutron, because the neutrons will have enough energy to conduct the next reaction. Are you guys able to understand? So it's not like other nuclei of uranium are not going to break. They may also undergo nuclear fission, but can they undergo nuclear fission chain reaction? No, because the energy of the neutron possessed by these particles will not be enough to support a chain reaction. I believe all of you guys are able to understand. Please tell me yes in the chat again, Shritama, Sagar, if you guys have been able to get it. So this is what is the logic of fissile fuel. Got it? So fissile fuel, we have 6 isotopes of uranium. 2 of them are considered natural, 238 and 235, and all 4 of them are artificial. Now guys, when you read some books, in some books it may also be written that uranium 234 is also naturally occurring. Actually it is not correct. It is not incorrect. Uranium 234 is also found naturally, but it is found in very small traces. It is found very small traces. Like if you look at pitch blende, the ore from where uranium is extracted, less than 0.01% is uranium 234. So most of the uranium 234, if it is needed, it has to be artificially produced. That's why I have written 234 under artificial isotopes. Excuse me guys. Under artificial isotopes. Got it? So this is what we have under natural uranium. So natural uranium is a combination of 238 plus 235. And within 238 and 235, there is one fissile fuel, that is 235. So technically what is needed in a nuclear reaction is uranium 235, because it is fissile in nature. It can undergo a nuclear chain reaction. Uranium 235. Now guys, here comes a problem. The problem is, even though natural uranium is combination of 238 and 235, but if you look at the composition of natural uranium, you'll be surprised to know that 99.3% of all the natural uranium that we have on Earth is uranium 238, which is non-fissile, which cannot undergo a chain reaction. And only 0.7% of all the uranium on Earth is uranium 235. So which isotope of uranium is required? Uranium 235, and only 0.7% of this uranium 235 is present on Earth. Rest is all uranium 238. So out of all the uranium that we have on Earth, only 0.7% is uranium 235. That means, suppose tomorrow if India imports natural uranium from some country, suppose tomorrow if India imports natural uranium from some random country, it could be from Russia, could be from Canada, could be from USA. If we import this natural uranium, suppose we get 100 kgs of natural uranium. Out of this 100 kgs, 99 kgs 300 grams would be uranium 238 only, and only 700 grams would be 235. Only 700 grams would be 235. So guys, you can understand, out of all the uranium, just 0.7% is uranium 235, rest is all 238. So guys, now when we use this natural uranium in stage 1, only 0.7% of the fuel is being consumed. Less than 1% fuel is consumed, because that is the only proportion of fissile fuel. Less than 1% fuel is being consumed in stage 1, less than 1%. And guys, what comes out as a residue? Is 99% of the fuel, that is uranium 238. Uranium 238 comes out as the residue. I hope all of you understand. So tell me, what do you think? Is this process appears to be a highly efficient process? Does this process looks like to be a very efficient process now? Of course not. This process is now having less than 1% fissile fuel. Out of all the fuel that we put, less than 1% is fissile. That means whatever fuel we are using, less than 1% is being consumed. 99% of the fuel is coming out as residue. So when 99% fuel comes out as residue, does it make this process a highly efficient process? Tell me yes or no in the chat. What do you think? Will this process be considered as a highly effective or efficient process? if only 1% of the fuel is being consumed into energy? Of course not. It is definitely not an efficient process of producing energy, because out of all the fuel that we are putting, less than 1% is being converted into energy. So guys, if you look at stage 1, just in this particular information, in this particular bracket, stage 1 is definitely not a very efficient stage. But let me introduce you to the second term. The second terminology that you have written, it's called fertile fuel. What is a fertile fuel? Please write down. Fertile fuels are those nuclear isotopes. Please write down fertile fuels. Fertile fuels are those nuclear isotopes which cannot undergo a nuclear chain reaction. Fertile fuels are those nuclear isotopes which cannot undergo a nuclear chain reaction. So they are those nuclear isotopes which cannot undergo a nuclear chain reaction. They cannot undergo a nuclear chain reaction. But they cannot undergo a nuclear chain reaction, but they are capable of converting themselves into another fissile fuel. So fertile fuels are those which cannot undergo a nuclear chain reaction, but they are capable of converting themselves into another fissile fuel. Basically guys, when you talk about fertility of a soil, a fertile soil is one which is capable of cultivating, right, crop, which is suitable for crop cultivation. Similarly, a fertile nuclear fuel is one which cannot undergo a chain reaction on its own, but you can actually cultivate a nuclear fissile isotope from it. Okay, so fertile fuels are those nuclear isotopes which cannot undergo a nuclear chain reaction, but you can use them to convert themselves into another nuclear fissile fuel. So guys, if I may give you the first example of fertile fuel. So guys, out of uranium 235 and uranium 238, 235 is fissile, 238 is non-fissile. It cannot undergo a nuclear chain reaction. But what if I tell you, students, that 238 is a fertile fuel? Uranium 238 happens to be a fertile fuel. That means uranium 238 cannot undergo a nuclear chain reaction, but you can actually convert uranium 238 into some other type of nuclear fissile isotope. So guys, it is a residue of stage 1. The residue of stage 1 is uranium 238, but it is not a waste. It is not like uranium 238 needs to be discharged and thrown out. It can actually be used to convert itself into some other fissile fuel. And guys, use your common sense. Which will be that fissile fuel that will be cultivated from uranium 238? That fissile fuel is plutonium. That fissile fuel is plutonium. So when you look at stage 2, in stage 2, uranium 238 is used. Uranium 238 is used, and this 238 is converted into plutonium. There are two again, plutonium also have 6 isotopes, but it can be converted into plutonium 239, 94, or plutonium 240, sorry, plutonium 239 or plutonium 240, right? Both of them are fissile. Both plutonium 239 and plutonium 240, both of them are fissile isotopes of uranium, fissile isotopes. They can undergo nuclear chain reaction. But the difference is plutonium 239 is mostly used for nuclear weapon systems. It can be used as a fissile fuel for making nuclear bombs, and plutonium 240 can be used for nuclear power plants, right? It can be used for nuclear power plants. So this is what we can do with uranium 238. So uranium 238 is non-fissile. It cannot undergo a nuclear chain reaction, but it does not make uranium 238 a waste. Uranium 238 can be converted into plutonium 239 or plutonium 240. And guys, this technique that is used to convert a non-fissile fertile isotope into fissile isotopes, this technique is known as breeding technique. this is what is the breeding technique. The breeding technique basically helps in converting a non-fissile fertile isotope into a fissile isotope. This is called breeding technique. I can even explain what is breeding technique. I can talk about alpha decay, beta decay and such, but guys, it is not required right now. And when we discuss alpha decay, beta decay, when we discuss the standard atomic model, I'll talk about this particular topic there. So I can revisit this topic and talk about how this breeding technique would ideally work. So this is called breeding technique. And now guys, what we can see, if I want to create a chain of events, the residue that comes out from stage 1 is now being used to breed the fuel for stage 2, And guys, now if you look at stage 1 and 2 together, don't you think now stage 1 and 2 together have a very high resource efficiency? Because whatever fuel is used in stage 1, whatever residue is produced, that residue is going to be thrown away. We can convert that residue into plutonium, and that plutonium can be used in stage 2 and further produce electricity. Tell me yes in the chat, guys. Stage 1 and 2, are you able to understand how stage 2 is nothing but an extension of stage 1 only? Tell me yes in the chat if you guys have understood. So stage 2 is nothing but an extension of stage 1. And now if I just repeat all the events happening in front of you. So like guys, let us start. Let us do it in one go. So in stage 1, what is the fuel? Natural uranium. Natural uranium is a combination of uranium-238 plus uranium-235. Out of uranium-238 and 235, 235 is fissile isotope, which can be converted into, or which can create a nuclear chain reaction. So in stage 1, uranium-235 is going to be consumed completely, converting all the uranium-235 into energy. What will be left as a residue is uranium-238. Uranium-238 as a residue will eventually be a fertile fuel. That means it cannot undergo a nuclear fission chain reaction on its own, but it can actually be converted into some other kind of fissile fuel. Now uranium-238, which is a fertile fuel, this is going to be converted into plutonium with the help of the breeding technique. And plutonium have two isotopes which are produced, plutonium-239 and plutonium-240. Both of them are fissile isotopes. Although plutonium is completely artificially produced, there are 6 isotopes of plutonium that can be generated: plutonium-241, plutonium-242, all these. So plutonium-238 is also there. So we can breed plutonium-239 or plutonium-240 from uranium-238. The technique is known as breeding technique, and in this, plutonium-239 is considered to be so unstable that it can be used only for making nuclear bombs, and plutonium-240 on the other hand can be used for making nuclear power plants. Are you guys able to understand? This is what we have under stage 1 and 2. And now when you look at stage 1 and 2 as a combination, you will see that all the fuel that India has imported for stage 1 is now being consumed fully for stage 1 and 2 together. Are you guys able to understand? This is what is the importance of stage 1 and 2, and how stage 2 is an extension of stage 1. I believe all of you guys have been able to get it. And now guys, if you are able to think closely, you can also understand why no country gave us stage 2 technology. Why no country was willing to give us the stage 2 technology? The reason was clear, because this breeding technique can actually also help us convert the non-fissile fertile uranium-238 into weapon grade plutonium. Are you able to see this? So why countries were not willing to share this technology with India? The reason is clear, because this technology can also help us to produce weapon grade plutonium. And this weapon grade plutonium, you guys can understand, if any country would take the risk of giving this technology to India, you can understand it will be somewhat making India nuclear weapon capable indirectly. Are you guys able to understand? So that is what the reason why countries were reluctant to give us the second stage technology. First stage technology, so many countries have partnered with India. Still so many countries partners with India to share their first stage technology, because they know with stage 1, India can only convert natural uranium and just 1% of that uranium into energy. But with stage 2, this is the stage that really helps you to expand your energy sphere of nuclear reactors. Are you guys able to understand? Tell me yes in the chat quickly if you have understood up till here. So this is stage 1 and 2, and this is the meaning of fissile and fertile fuel as well, right? This is the meaning of fissile and fertile fuel, and this is what we have under stage 1 and 2. Now guys, we have got the third stage. Do we have nuclear reactor of which stage, Sagar? Stage 1, 2 or 3? Stage 1, yes, stage 1 we have. Right after this we'll talk about nuclear reactors only. So stage 1, yes, we have nuclear reactors. We have indigenized nuclear reactors of stage 1, and they are also being working. They are working, they have been set up at commercial scale also, producing up to 700 megawatts of energy. They are there. When it comes to stage 2 reactors of India are still in the process of being developed. I must have told you in the previous class that we are expecting by September 2026, as per the latest declaration, by September 2026, our second stage commercial reactor will start working. Although the prototype reactor was built in 1985 itself, second stage, right? So I hope all of you guys are able to recall. This is stage 1 and 2, and this is the status of natural uranium and plutonium. Now, guys, what about the third stage? We have got the third stage, that is thorium powered. And what about the stage 3? So if I tell you, the moment I tell you what type of fuel is thorium, the moment I tell you what kind of fuel is thorium, it should be clear in your mind how this entire process is going to affect thorium based energy. So guys, what if I tell you that thorium is also a fertile fuel? Thorium is also a fertile fuel. The moment I tell you that thorium is also a fertile fuel, thorium is atomic number 90, mass number 232. If thorium is also a fertile fuel, what would that mean, guys? It means thorium alone cannot generate energy. Thorium alone cannot be used for making electricity, cannot generate energy because it is fertile fuel. Yes, but being a fertile fuel, thorium can be converted into some other fissile fuel, right? So thorium by nature is non-fissile, right? It is non-fissile, and because it is non-fissile, it cannot produce energy on its own. But because of its fertile nature, thorium can be converted into uranium 233. What was uranium 233? Look at this, guys. Uranium 233 is an artificial form of uranium which is fissile. It's an artificial form of uranium that is fissile, uranium 233, and this uranium 233 can actually be converted into energy. So guys, you remember I told you in the previous class when we discussed the 3 stages, I have told you this, that to produce thorium based energy, we require 2 types of technologies. We require 2 types of techniques for producing thorium based energy. One is a moderator based reactor, and second is breeding technique. So now I hope you can recall the breeding technique is required for thorium to convert the non-fissile thorium into fissile uranium 233. And once we have got the uranium 233, we'll use the moderator based reactor. We'll use the moderator based reactor of stage 1. So this moderator based reactor comes from stage 1 and the breeding technique comes from stage 2. So are you guys able to recall that for producing thorium based energy, we require 2 set of technologies? If you do not recall, I can show you. I must have written it here in my annotations. It should be here already. Look at this. To produce thorium based technology, we require to produce thorium based energy, we require 2 set of technology: a moderator based reactor that is going to be supplied from stage 1 and a breeding technique that will be supplied from stage 2. You guys can see. So here it is clear that how we need the stage 1 and 2. How do we need the stage 1 and 2? The stage 1 reactor is required for converting uranium 233 into energy, and stage 2 reactor technology is required for converting thorium 232 into uranium 233. Guys, are you able to understand the meaning of all these terms now? Are you able to understand? So guys, the plutonium reactor, it says breeder reactor. You guys know that breeding because it is a process where breeding is really done, right? So this is the entire logic behind the fissile fuel, fertile fuel, and the logic behind the entire 3 stages. So I hope now the 3 stages are much more clear, that how the thorium reactors is also a breeder reactor and the stage 2 reactor is also a breeder reactor. I hope all of you guys are able to get it. This is what we have under the 3 stages, and also the meaning of fissile fuel, fertile fuel is also clear to all of you. So we have understood what is the meaning of fissile fuel. Just to give you a quick revision, the nuclear isotope that is capable of undergoing a nuclear chain reaction. Fertile fuel, those isotopes which cannot undergo nuclear chain reaction but can be cultivated or can be converted into some other fissile fuel. Uranium-238 and thorium-232, both of them are fissile fuels. Got it all of you? Acha, what is interesting for thorium is, because thorium is a fissile fuel, thorium is a fertile fuel, thorium is considered to be non-fissile for nuclear bombs also. So nobody can create nuclear bombs from thorium. And uranium-233 that is produced from thorium, even this uranium-233 also does not last for much longer. It has to be immediately converted into energy, right? So this is what is the entire situation of fissile fuel, fertile fuel, and the 3 stages. I hope all of you guys are able to get it. Now we have understood the meaning of fissile fuel, fertile fuel, and now let's see what is the meaning of the word enrichment. And there is a chance that UPSC would ask question on enrichment. Why? Because whenever we talk about nuclear weapon systems, whenever we talk about nuclear weapon systems, there is a term enriched uranium that often comes. Okay, so let us talk about enrichment, guys. Let's see what is the meaning of enrichment. So before I talk about the meaning of enrichment here, let us first understand the working of a nuclear reactor, or how the logic of nuclear reaction works. So guys, we have something called natural uranium, right? We've got something called natural uranium, and we know that natural uranium is a combination of uranium-235 and uranium-238, out of which uranium-238 is fertile and uranium-235 is fissile, right? So guys, if I ask you how much is the percentage of fissile fuel in natural uranium, what will that be? If I ask you how much is the percentage of fissile fuel in natural uranium, what would that be, guys? What answer will you give? If I ask you how much is the percentage of fissile fuel in natural uranium, 0.7%, just 0.7%. So we all know, very good Sagar. So this is 0.7% and this is 99.3%. So if I ask you what is the percentage of fissile fuel in natural uranium, you will say 0.7%. 0.7% is the percentage of fissile fuel in natural uranium, right? So guys, if you talk about natural uranium has got only 0.7% of fissile fuel, only 0.7% of fissile fuel. Now guys, just think about it. Suppose I want to make a nuclear bomb. Let's suppose I want to create a nuclear bomb, and for this nuclear bomb suppose I want to create a nuclear bomb, and for this nuclear bomb I have natural uranium with me. Now this natural uranium, if I put in a nuclear bomb, I know that natural uranium will be fissile only for 0.7% of the total fuel. So it means if I put this 100 kg of natural uranium in a nuclear bomb and drop it on the enemy country, out of the 100 kilograms of natural uranium that I have put, only 0.700 grams, only 700 grams are going to be converted into energy, right? Rest 99.3% would remain completely unutilized. So do you think this kind of a nuclear weapon can be of any purpose? Can it really make the enemy scare away? No, because the enemy knows that India does not have the technology. Suppose I do not have the technology of converting the non-fissile fertile fuel into weapon grade plutonium. So when I do not have the technology for that and I only have natural uranium, that means the enemy would never be scared with this type of figures, right? Because they know that whatever nuclear fuel I'm going to put, they would be just 0.7% fissile fuel. So guys, when it comes to natural uranium is not suitable. It is not suitable for nuclear weapon systems. Nuclear weapon systems does not require natural uranium. And this is also the reason why countries were willing to give us stage 1 technology, because they know that stage 1 is natural uranium powered. India would not be using that natural uranium for any weaponization purpose. because natural uranium is not suitable for nuclear weapon systems. But guys, here comes weapon grade uranium. Weapon grade uranium. The weapon grade uranium is supposed to be such a uranium which has got the fissile fuel percentage up to 90%, which has got the proportion of fissile fuel up to 90%. That means it's not 0.7%. They have increased the proportion. Weapon grade plutonium is one where the fissile fuel proportion has been increased to 90%. That means out of 100 kilograms of weapon grade uranium, 90 kgs would be uranium 235. 90 kgs are going to be uranium 235. So the question that you should ask here, how it is possible to increase the percentage of uranium 235 from 0.7% to 90%. How it is increased from 0.7% to 90%. Guys, this is known as enrichment. This is known as enrichment. So please write down what is enrichment. I'll explain the process of enrichment right after this. Write down enrichment, guys. Write down enrichment is a process of isotope separation. Enrichment is a process of isotope separation. Enrichment is a process of isotope separation. Okay, so enrichment, it is a process of isotope separation. Enrichment is a process of isotope separation where a fissile isotope of uranium 235, a fissile isotope of uranium 235 is separated. A fissile isotope of uranium 235 is separated from a fissile isotope of uranium 235 is separated from fissile isotope of uranium 235 is separated from natural uranium. Fissile isotope of uranium 235 is separated from natural uranium and then increased in proportion for various applications Okay, so the first point is it is separating uranium 235 from natural uranium and then increasing its proportion for various applications. So guys, when it comes to weapon grade, we require 90% uranium 235. For power generation, the enrichment level could be up to 5 to 7%, up to 5% or maximum up to 7%, right? So for power generation, we may increase the proportion of uranium 235 up to 5% or maximum up to 7%. And for weapon grade, we have to increase it to 90%, right? So this process is called enrichment, where we separate the uranium 235 from natural uranium and then increase its proportion to whatever percentage we require. Got it? This is called enrichment. Now guys, you may ask how exactly enrichment works. So guys, enrichment, this process actually happens with the help of a device known as centrifuge. There is a device called centrifuge, and the centrifuge is the actual equipment which is used for enrichment. Centrifuge. And centrifuge works by the principle of centrifugation. It works by the principle of centrifugation, or guys, you can say centrifugal force. Centrifugation, which is nothing but centrifugal force. I'll explain all these things, guys. Right, centrifugation or centrifugal force. I'll explain this. And this is something that I'm very sure all of you have seen at least once in your life. At least once all of you must have seen. In fact, you must have seen multiple times, but at least once all of us have seen. Now, I'll take the example of nuclear centrifuge later, but let me first explain what is centrifugation. So, guys, have you ever seen the traditional method of making milk, cream or butter from milk? Have you seen the traditional method of making cream and butter from milk? In traditional method, they call it the Bologna method, if you guys must have heard, right? So what we have we basically, so traditionally what used to happen, how we separated milk from cream or butter from cream, cream from milk and all these things. So traditional method was that you would put the milk in a container, large container. You put a wooden spindle, एक लकड़ी का एक डंडा होता है, wooden spindle. The wooden spindle would have some spokes emerging on all sides, and then you coil the spindle with some rope. And then what you do, you keep pulling one rope alternatively like this, and the milk keeps churning. The milk keeps churning. And when you keep doing it for few minutes, because we know that milk is not just water, guys. Milk is made up of various components. Milk is actually made up of milk fats, milk sugar, milk proteins, and the fats of milk are also of different density, proteins are of different density. So milk is made up of so many other things. So what happens when you start churning the milk, the denser part, the heavy part of the milk, that is the milk fat, it gets accumulated at the center. The denser part of the milk goes to the center, and the lighter part, the less dense part, which mostly contains the milk, sugar and proteins, they go to the periphery. They go to the edge. So have you guys ever noticed, in fact, in school syllabus also, in the CBSE syllabus also, it is mentioned that students or school students should go to some factories. So I remember when I was a kid, we went to the Mother Dairy factory. Mother Dairy is a popular milk brand in Delhi, right? It is also present in other places as well. So we went to the Mother Dairy factory, I remember. And in the Mother Dairy factory, they showed us the centrifuge. That time we did not really understand what was a centrifuge, right? So in that centrifuge, it was a very large container, and they would be pouring milk into the centrifuge. And as the centrifuge works, as the centrifuge starts spinning, what will happen? Suppose this is the liquid, right? The moment centrifuge starts spinning, the moment the centrifuge starts rotating, we will notice that all this liquid starts getting separated. The most dense part, the dense part of the liquid will go accumulate at the center. The lighter part of the liquid goes to the periphery. And in between also there are layers and layers of different components based on density. The denser part goes to the center and lighter part goes to the periphery. So you know that from milk, you extract so many different things. You extract skimmed milk, you extract whey protein, you extract, butter, cream. So when you start spinning it, at a certain speed, because of milk being a composition of so many different things, they all get separated and makes rings like substances. So from those rings, they keep extracting different components, and they take out all these components of the milk from that centrifuge. So this is also a large centrifuge, and the process is called centrifugation. Are you able to understand? One more example of centrifugation, if you guys have started geography already, you may be knowing that even our planet Earth, when it was formed, initially it was in the molten state. But as the planet Earth started spinning, the denser part of the Earth got accumulated at the center, making the core, inner core, which is densiest, and the lighter part, mantle, crust, it got to the periphery, and the lightest part, atmosphere, went to the periphery. Are you guys able to visualize? So even our planet Earth is a very good example of liquid centrifugation. So guys, whenever liquid centrifugation occurs, whenever liquid centrifugation happens, in a case of liquid centrifugation, the denser part comes to the center, and the lighter part goes to the periphery. In the case of liquid centrifugation, denser part comes to the center and lighter part goes to the periphery. Are you able to understand? Denser part is at the center, lighter part is at the periphery. Tell me yes in the chat if you guys are able to follow. Tell me yes in the chat, guys. Denser part is at the center, lighter part is at the periphery. This is what is liquid centrifugation. Remember, in liquid centrifugation, denser center, lighter part periphery. Guys, the centrifugation process can also happen for gases as well. We also have gas centrifugation as well, right? Because if you talk about milk, it is liquid centrifugation. Acha, by the way, there is also blood. Blood centrifuge is also there. If any one of you has ever donated your blood platelets, your blood plasma, you would notice that when the blood is taken, the machine is very different in that case. When the blood is taken, the blood goes into a centrifuge, and the centrifuge will start spinning. And we know that blood is also made up of multiple things. Blood is made up of blood cells, blood is made up of blood plasma, right? And cells are also, platelets are different cells, red blood cells are different, white blood cells are different, all of them are different cells. So we can actually differentiate the blood into different components also by the simple process of liquid centrifugation. So if any one of you has ever donated blood platelets, blood cells, it is liquid centrifugation that occurs in that case also, right? Liquid centrifugation. So this is what we have under liquid centrifuges. Then guys, next is gas centrifuges. Gas centrifugation is also a centrifugation process where instead of putting liquids, we put gas, and we separate gas into different components. So like guys, when you look at air is not a single type of a gas. Air is a combination of nitrogen, oxygen, argon, CO2, and so many dust particles. So when you take air, you can actually separate nitrogen, oxygen from air also, and that method would be called gas centrifugation. But the only difference is that in gas centrifugation, the lighter part comes to the periphery and the denser part goes to the, lighter part comes to the center and denser part goes to the periphery. Lighter part comes to the center and denser part goes to the periphery, right? In the case of gas centrifugation, that is the only difference. So lighter is at the center and denser goes to the periphery in the case of gas centrifugation. Remember this. Now, of course, UPSC may not ask the difference between gas and liquid centrifugation, but if they ask about centrifugation in general, you should know gas and liquid. I can also explain why gas and liquid have different orientation, why denser at the center and in the case of liquid and lighter at the center in the case of gas, because I'm a mechanical engineer also, so I have studied the concept of compressive stress and shearing stress. So it is based on some basic levels of mechanics and physics. I don't think UPSC will ask that, okay? But if you still want to know, you can write it down on the chat and I'll be happy to explain this, okay? So on the group you can ask these kind of questions, I'll be happy to explain, okay? So this is what we have under gas centrifugation and liquid centrifugation. Got it, guys? Now when you talk about uranium enrichment, uranium enrichment is an example of gas centrifugation. Uranium enrichment is an example of gas centrifuge. So what we do basically, we convert natural uranium. For the process of uranium enrichment, natural uranium is heated into a gas. It is converted into gases, right? How is it converted? We normally react uranium with fluorine. So the fluorides of uranium are in the gaseous form. And then guys, we put it in a gas centrifuge. The gas centrifuge starts running. Uranium 235 being lighter will get accumulated at the center, and uranium 238 being heavier will get accumulated at the periphery, right? Are you able to understand? At the periphery. So this is how we can differentiate. And once we get all the uranium 235 at the center, we'll simply keep extracting the uranium 235. We keep extracting uranium 235 from all the natural uranium we have, and then we club all this uranium 235, combine it together and increase the proportion to whatever percentage we want. Suppose if we want to put 90% of the fuel with uranium 235, we'll take 90 kilograms and put it in the warhead of a nuclear bomb. If you want to produce electricity, we may increase it to 5% and use it in a nuclear power plant. That is how easily the process of fissile or from fissile to enriched fissile uranium works. Are you guys able to understand? Please tell me yes in the chat if you guys have understood. This is the process of enrichment, and the name of the device is called centrifuge. The technique is called centrifugation. I hope all of you get it. This is what we have under the working of a nuclear fuel. So now we have understood the meaning of enrichment, fertile fuel, fissile fuel. Now guys, you can also try these answers. Now we are at the last part of our discussion of a nuclear reactor. So guys, this is the schematic diagram of a nuclear reactor. If you guys have noticed, we have discussed almost everything about reactions, but you have still not learnt the meaning of PHWR, pressurized heavy water reactor. We haven't learned that. We have not learned the meaning of moderator. We have not learned the meaning of coolant. We haven't learned any of these things. Neither we have got the meaning of all these things also. So now the last part of our discussion is only to talk about these technicalities, right? So we have got a schematic diagram of a nuclear power plant. This diagram is of a stage 1 nuclear power plant. This diagram that you see, it is probably stage 1 nuclear power plant. Okay, got it all of you? Now guys, this is the last part of the nuclear technology part. After I finish this, then we only have some current affairs, right? Current affairs and all these things, and we'll see what are the current affairs. So we'll cover everything in this particular discussion, right? Technology part would be covered here. After this, we only have some current affairs, some polity issues, and some IR related issues of nuclear energy. So guys, let us start. So can anyone write down the short form of stage 1 reactor? What is the name of the stage 1 reactor? Can anyone write it in the chat? Likho jaldi se. What is the name of the stage 1 reactor? Because this is a diagram of the stage 1 reactor. This is a diagram of the stage 1 reactor. What is the name of the stage 1 reactor? Can anyone write? Sagar, Shitama, if any one of you can write. Stage 1 reactor. What is the name? Short form. In short, what have we written that? PH something we have written. Stage 1. This is the image of stage 1 reactor. The name of the stage 1 reactor is PHWR. Right? This is the name of the stage 1 reactor, PHWR. If I write down the full form, it is pressurized heavy water reactor. Pressurized heavy water reactor. Guys, let us break it down. It says pressurized heavy water reactor. What is the meaning if I try to break it down? It means it's a nuclear reactor. That contains heavy water. Heavy water, you guys know. We write heavy water as D2O, right? Not H2O, because H2O is light water. Heavy water is deuterium, made up of heavy hydrogen, heavy water. So it's a nuclear reactor which has heavy water D2O, and that too at high pressure, right? That too at high pressure. So the name itself is clearly saying pressurized heavy water reactor. It's a nuclear reactor containing heavy water at high pressure. We call it pressurized heavy water reactor. So it's a nuclear reactor containing heavy water at high pressure. Now guys, what is the logic? What is the logic of having heavy water at high pressure? You can even see, if you have understood the meaning here, you can see that there is something called pressurizing system also mentioned here. Can you notice in the diagram, there is something called pressurizing system, which is simply applying high pressure into the reactor, right? Now guys, we'll see this relationship, we'll see the diagram later, but first let us understand what is the meaning of pressurized heavy water. What is really going to change if you put pressure on heavy water? What is really going to change? So guys, here I have got a question for you, because both of you are not from science background. So even if you give me a wrong answer, it will not be a problem. Tell me, suppose I'm here in Delhi, right? And let's suppose you guys appear for the civil services exams and you guys qualify the exam. Let's hope that you qualify the exam in the very first attempt, and you go to Mussoorie for your foundation course, right? You go to Mussoorie for your foundation course. I hope all of you guys are aware, Mussoorie has the Lal Bahadur Shastri Academy, National Academy for Administrative Studies. So you go there, right? So now you go to Mussoorie, and let's suppose coincidentally I'm in Delhi, you are in Mussoorie, and coincidentally we both are boiling water. I am boiling water in Delhi, you are boiling water in Mussoorie. For some reason you are boiling water in Mussoorie and I am in Delhi. Let's suppose everything else is same utensil, same quantity, same gas stove, every other thing is same. Tell me whose water will boil first, the one in Delhi or the one in Mussoorie? What do you guys think? Whose water should boil first? The one in Delhi or the one in Mussoorie? Whose water should boil first? What do you guys think? Sagar, you think it could be Delhi? Shritama, what do you think? Or will it be Delhi, Mussoorie, or both at the same time? Right? Will both the waters will boil at the same time? The answer, Shritama, you also think it is Delhi. The reason I think why you are thinking Delhi, because Delhi is comparatively warmer, right, compared to Mussoorie, and because it is warmer, of course, the boiling point of water may be reached at the earliest, right? That's what you might be thinking. Achha, by the way, what is the boiling point of water? The boiling point of water is 100 degrees Celsius, right? 100 degrees Celsius is the boiling point of water, right? 100 degrees. But you know what? This 100 degrees Celsius boiling point is actually based on a condition. इस पे condition है. There is a condition attached to it. The condition is the water boils at 100 degrees Celsius at 1 atmospheric pressure. When the pressure is 1 atmosphere, in this condition the water boils at 100 degrees. So the boiling point of water is not just 100 degrees, it is 100 degrees at 1 atmospheric pressure. That's the condition for boiling water. Okay, so the boiling point of water is 100 degrees at 1 atmosphere. Now guys, let us try to understand what is this logic of atmosphere. So imagine this is our atmosphere, this is the layer of the atmosphere, and let's suppose these are the relief features of Earth. Okay, this is the highest point on Earth, let's call it point A. This is the deepest point on Earth, let's call it point B, and this is the sea level, let's call it point C. We have three different locations, A, B, C, right? Now guys, can anyone tell me between A, B, C, which place is going to have the highest atmospheric pressure? Highest atmospheric, or tell me lowest atmospheric pressure first. Which place is going to have the lowest atmospheric pressure between A, B and C? Lowest atmospheric pressure first. Sagar, you are saying B and Shritama is saying A. Now the answer is A. A is going to have the lowest atmospheric pressure. You know why? See, it's very simple. You don't have to mug up these things. These are very simple concepts. Just try to understand. Shritama, you want to say something? Alright, so what happens? Imagine if I'm standing here. I'm standing here on the ground. Above me, whatever atmosphere is there, atmosphere is there, that atmosphere might be applying pressure. Above me, all that atmosphere would be applying pressure on my head, right? So that is nothing but atmospheric pressure. So if I'm standing here, the atmosphere, the thickness of atmosphere. So imagine if I'm standing here at point C, the thickness of atmosphere above C is this much. This much is the thickness of atmosphere above the point C. When I'm standing at point A, this much is the thickness of atmosphere above me. This much is the pressure head above A. And when you are at B, this much is the water head for B, and then this much is the air head for B. So Sagar, think about it and tell me again, where do you think least pressure will be applied? Where we have least mass of atmosphere above us? Simple. So the least atmospheric pressure would be at A because least pressure is applied. And Sagar, you only answer where are we going to have maximum atmospheric pressure? Highest atmospheric pressure would be at which place? A, B or C? It will be at B. Perfect. B is going to have highest atmospheric pressure. So A will have the least atmospheric pressure, B will have the highest atmospheric pressure. And guys, if you have started geography, you may have learned that at point C, at the point C, we have 1 atmospheric pressure. 1 atmospheric pressure would be at point C. 1 atmospheric pressure would be at point C. So point C will have 1 atmospheric pressure. Point A will have a low atmospheric pressure, and point B will have highest atmospheric pressure. You know, 1 atmospheric pressure by definition, it simply means it is the pressure of the atmosphere observed at the equator at the mean sea level. So when you are standing at the equator, and that too at the mean sea level, whatever atmospheric head you feel, it will be 1 atmospheric pressure. So let's consider C is close to 1 atmospheric pressure, A is less than 1 atmosphere, and B is of course more than 1 atmosphere. Now guys, what is the boiling point of water? 100 degrees Celsius at 1 atmospheric pressure. That means if you are boiling water at sea, at the location of sea, here the water will boil at 100 degrees. So if you are standing at the equator at the mean sea level, the water will boil at 100 degrees at this point, at this location. But what will happen when you take the same water to A or B? When you take the same water to A or B, what will happen here? So remember guys, with increase of pressure, the boiling point of water also increases. With decrease of pressure, the boiling point of water also decreases. Remember this relationship. Boiling point and pressure are directly proportional. If you increase the atmospheric pressure from 1 atmosphere, the boiling point will also increase. If you decrease the atmospheric pressure, the boiling point will also decrease. So guys, if the pressure at B is greater than 1 atmosphere, the water will boil at B later because the boiling point will also increase. Let's suppose it increases to 120 degrees Celsius. So now the water, so if you go in a submarine, if you travel in a submarine and go to the edge or go to the end of the or deepest point on earth, and suppose there you think of making Maggie, you start boiling water, and what happens? The water boils later at 120 degrees Celsius because the atmospheric pressure is high. Suppose you go to the highest point on earth, on point A, and there you think of cooking Maggie for you, the water will boil, let's suppose, at 80 degrees Celsius, right? The water will boil at 80 degree. So guys, tell me, between Delhi and Mussoorie, Mussoorie is of course at a much high altitude, whose water will boil first, Delhi or Mussoorie? Tell me guys now quickly, whose water should boil first, the one in Delhi or the one in Mussoorie? In Mussoorie, of course, the boiling point is going to be lower than 100 degrees. So where the water will boil first? Sagar, what do you think? It is also Mussoorie, right? Shidama, very good. So answer is Mussoorie. In the water will boil first in Mussoorie because it has low boiling point. Now you know what? UPSC have asked a similar sounding question once, right? Tell me, Sagar, what is the confusion? What is the confusion, Sagar? Chalo, I'll share this question that has been asked in UPSC previously, and then I'll come to your doubt. You can write the your question in the chat right now. See, if you want, you can even unmute yourself. अगर आप चाहते तो unmute भी कर सकते हैं, right? Okay, why the water is going to boil faster? Okay, see, the point is, if the boiling point is lower, don't you think when we start heating, it will be first 80 degree that would be achieved, then from 80 to 100 degrees. So why the water will boil first in Mussoorie? Because 80 degrees is easier to reach than 100 degrees. That's basically the logic. Sagar, are you able to understand? So water is likely to reach 80 degree much faster than 100 degrees, and that's why the water will boil first in Mussoorie, right? So that's the point. Now guys, UPSC have asked one question. The question is, when you talk about boiling water, you understand that water will boil first where atmospheric pressure is low. So lower the atmospheric pressure, lower is the boiling point, water is going to boil first there. But guys, UPSC asked a different question. They asked a question, why does it take longer to cook food in Kashmir than in Delhi? Why does it take longer to cook food in Kashmir than in Delhi? See, the question is different now. If you are asking only for boiling water, the water will boil first in Kashmir because it is at a high altitude. But when you ask about cooking food, I hope you understand, food when it is cooked in water, the food is cooked only with not just the boiling of water, but also the heat of the water. Like for example, if ever you go to Ladakh, if you ever plan to go to Ladakh, many of you might be having an objective of going to Ladakh. Many of you might be having a bucket list where you want to travel to Ladakh. If you ever go to Ladakh, you will find out that in Ladakh, a lot of people are selling, Maggi. Maggi is being sold as a very staple food there because it is quick to make, right? But you will find out that many a times the Maggi that they are cooking, in fact, most of the times it is never fully cooked. Even though they may be cooking it for 10-15 minutes, what Maggie says 2 minutes, but they may be cooking for 10-15 minutes, but still the Maggie is never fully cooked. वो कभी पूरी तरह से cook नहीं होता है. The reason why the Maggie is never fully cooked, because the water never reaches 100 degrees Celsius temperature there. Because when you start boiling water, the water may boil at 80-90 degrees, never reaches 100 degrees. So you have to keep boiling the water or keep the food for a much longer duration in the utensils. And even when you keep it for a very long duration, there is a chance that the food may never get fully cooked. Whereas if you are living in a plainer area close to the sea level, the water will boil at 100 degrees Celsius, and that means the heat at which the food is cooking, it is greater, and that's why the food gets cooked early at lower altitude. And guys, you understand the logic of pressure cooker also now. In a pressure cooker, we basically close the food and water in a cooker, and that cooker increases the pressure with time. So pressure cooker, as the name suggests, it's a cooker that cooks food not only at high temperature but also at high pressure. Because suppose normally if I cook a food in an open utensil, the water boils at 100 degrees. But in a pressure cooker, the pressure is increased inside the cooker in such a way that the water boils at 110 degrees. And if the water boils at 110 degrees, you can easily understand at 110 degrees, the water will remain in the liquid stage, the food gets cooked even faster, and that's how pressure cookers are able to cook food faster than any other way, because they are cooking food at a higher temperature beyond 100 degrees Celsius. Are you guys able to understand? Are you able to understand the logic of pressure cooker also? So pressure cooker works on the principle of this manipulation of temperature boiling point by increasing the pressure. I hope you guys are able to understand. So why does it take a longer time to cook food in Kashmir than in Delhi? Because Delhi is closer to the sea level, the boiling point is 100 degrees, but in Kashmir the boiling point is lower, and that's why you have to cook food for a longer duration to cook it properly. Otherwise the food may not be cooked properly. It will remain raw, like what happens with Maggie. Whenever you eat Maggie in Ladakh, you will find that the Maggie is never fully cooked, right? The reason is because even if the person is cooking for 15 minutes, it is never able to have the right temperature so that it cooks properly. I hope all of you guys are able to understand. This is the relationship between pressure and boiling point. Pressure and boiling point. Now guys, if you have understood this concept, let us play with this concept once. Okay, I'll ask you a few questions and let's see if you can answer. So guys, let's suppose I have this bottle of water. You can see this is half filled, right? Now when you see this bottle of water, suppose I want to boil this water. But unfortunately I do not have any heating element. I don't have anything to heat, but I've got a vacuum pump with me. Don't have anything to heat, but I've got a vacuum pump with me. Tell me guys, is it possible for me to boil this water with the help of a vacuum pump? Can I boil this water with the help of a vacuum pump? Of course the answer is yes. That's why I'm asking it, right? So you can boil this water not with just heat but also with a vacuum pump. But the logic is, imagine if I put a vacuum pump at the top and start sucking all the air out. When the air is going to be sucked out, a time will come when the pressure inside this bottle will start decreasing. A time will come when the pressure would get decreased to such an extent that the boiling point of this water will decrease to the room temperature. I hope you guys are able to understand, because as we decrease the pressure, the boiling point also decreases. So what if I start decreasing the pressure of this bottle in such a way that the pressure is decreased to such an extent that the boiling point also decreases and becomes equal to the room temperature? What will happen when the boiling point of this bottle, this water touches the room temperature? I will start noticing that this water starts boiling. This water will start boiling because the pressure has been decreased to such an extent that this water may be boiling at room temperature itself. And guys, if you go and touch this bottle at that time, you will not feel heat. Although you will notice that the water is boiling, but you will not be feeling any heat because the water is boiling at the room temperature itself. Are you guys able to understand? And what if I decrease the pressure further? The entire water will even vaporize. It will turn into steam, but that steam would be also at room temperature. Are you guys able to understand? Please tell me yes in the chat. Sagar, did you understand this? Shitama, Sagar, what do you guys think? You understand? This is what is the relationship between pressure and boiling point. This is what is the relationship between pressure and boiling point. Got it, all of you? This is what we have under pressure and boiling point, and this is exactly what is happening with pressurized heavy water reactor now. So now when you look at pressurized heavy water reactor, it is a heavy water that is kept at high pressure. What we can infer just now with high pressure heavy water is, it's a heavy water kept at high pressure. That means the boiling point of the heavy water has been increased. Now guys, just to give you a small point here, for heavy water, its boiling point is 101.4 degrees Celsius. Right? Heavy water's boiling point is naturally 101.4 degrees Celsius. This is the natural boiling point of heavy water, 101.4 degrees. Right? Yes, instead of heavy light water, they are using heavy water. That's why it says pressurized heavy water reactor. So naturally the heavy water, it is having a boiling point at 101 degrees Celsius at 1 atmosphere. Right? This is the boiling point of heavy water at 1 atmosphere. And guys, because it says pressurized heavy water reactor, you'll be surprised to know in a pressurized heavy water reactor, the boiling point is increased to 900 degrees Celsius. And now you understand how it is increased to 900 degrees Celsius by simply increasing the pressure. We increase the pressure of the reactor to such an extent so that the water will boil not at 101 degrees but at 900 degrees. At 900 degrees. So you understand the meaning of pressurized heavy water reactor. It's a nuclear reactor that uses heavy water at high pressure, and the logic is increase the pressure of heavy water up to 900 degrees Celsius. 900 degrees Celsius. Acha, one more example, one more question I'm having in my mind. Let's see if you guys can answer this also. So one question I asked you, that what if I put a vacuum pump on top of this bottle, and is it possible for us to boil the water at room temperature? The answer is yes. Right? With the help of a vacuum pump, we can boil this water. Another question that is in my mind, guys, you know that India is planning to send its first astronaut in space, right? Very recently in the Axiom 4 mission, you all must have seen, Sudhanshu Shukla became just the second Indian to be sent out in space by India, right? Although it was an American mission, but India ISRO was a part of this mission, right? But now in 2026-27, India may send its astronauts with the help of our own mission, our own rocket. We are going to send astronauts in space, Gaganyaan. Now guys, let's suppose you get selected as one of the astronauts. Of course, the people are already selected. They are mostly Air Force background people, but still, suppose you get selected as one of the astronauts. So the moment when you go reach in space, you would realize that in space, you will be given a proper space suit. You can't wear your normal clothes in space. It's not like you have got a suit stitched for your wedding and you thought that let me wear this particular suit in space. No, you have to wear a proper space suit. That proper space suit is basically going to maintain the right pressure in your inside the space suit, which will be helpful for you to survive in that extremely low pressure of space. As we all understand, as we keep rising up, as we keep climbing up, the pressure keeps decreasing. As we keep climbing up, the pressure keeps decreasing. The moment when you cross the atmosphere, there is zero pressure. There is zero pressure in, when you cross the atmosphere. And at that pressure, just imagine what will happen to your body. Suppose if accidentally somebody gets exposed to zero pressure. Suppose if somebody accidentally gets exposed to the zero pressure, we know that 70% of our body is water. All this water in our body will get vaporized in a second. All this water will get vaporized in a moment. The blood vessels on the surface, the superficial blood vessel, they will start rupturing like anything. And all the bodily fluids will start getting vaporized. This is going to happen if somebody accidentally opens up the space suit. Right? Of course, see, freezing may also happen. But at the same time, because the pressure is zero, the water will also vaporize. And see, vapors of water may also get frozen. Vapors of water can also get frozen. That's called snow. Snow is basically water vapor getting frozen is snow. So that freezing may also happen, but first vaporization and then freezing. So all these things are going to happen exactly at the same time. So you can just imagine that how dangerous it could be when you are in space without a proper space suit. So the purpose of the space suit is actually to keep you at the right pressure levels so that your body can function properly, your body can remain 70% water. I hope you guys are able to understand. This is the importance of pressure. So pressure and boiling point, I hope all of you got the relationship here. Right? Please write down yes in the chat one last time so that I understand that you have got the entire understanding of the concept here. Alright, perfect, perfect. So this is what we have. Now guys, I am deleting this particular part of the slide because now you have understood the meaning of the relationship between pressure and boiling point, right? This particular part I am deleting. And now, before I go ahead and talk about the next topic, you have understood the meaning of pressurized heavy water reactor. Now, if you talk about a nuclear power plant in general, to compare a nuclear power plant, let me quickly give you a schematic. Let me quickly give you a schematic presentation of a thermal power plant first. Let me talk about a thermal power plant first, and then we'll see how exactly a nuclear power plant differs from that thermal power plant, right? So if any one of you has ever been to a thermal power plant, if you have ever been to a thermal power plant, you would notice that in a coal, I'm talking about coal-based thermal power plant. In a coal-based thermal power plant, the most important component of a thermal power plant is boiler. Boiler is the most important component of a thermal power plant. Boiler is the most important component of a thermal power plant, a boiler. And this boiler is normally heated to a temperature of 500 degrees Celsius. We all know water boils at 100 degrees, but the boiler is heated at 500 degrees Celsius. And this boiler is kept with water. We keep water in the boiler, H2O, and which is heated at 500 degrees Celsius. And we know that we are using coal for it. So coal is typically used to heat the boiler. So coal is typically used to heat the boiler, and the boiler is normally heated up to 500 degrees Celsius, right? Now we know that water boils at 100 degrees. So what is done at 500 degrees Celsius? So what we do, we heat the water to steam at 100 degrees, and once the steam is produced, we keep reheating the steam up to 500 degrees Celsius. So we keep reheating steam to 500 degrees Celsius, right? So we keep reheating the steam up to 500 degrees Celsius, and then this 500 degrees Celsius of steam, is then transferred. So this 500 degrees Celsius steam, we may call it superheated steam, right? So we are heating the steam to a superheated level, right? 100 degrees pe we get the steam, but when you heat it to 500 degrees Celsius, you are superheating the steam. So the steam gets superheated, and this superheated steam gets supplied towards the turbine. The turbine is nothing but a fan with these kinds of blades. The moment when the superheated steam hits the turbine blade starts rotating. The turbine blades, they start rotating, and as the turbine blades rotates, they power a generator attached to them. They would power a generator, and this generator will produce electricity that will be supplied to the grid. Got it? The electricity is going to be supplied to the grid. Now, from this turbine, the used steam, the steam that has already been used, it goes to another container known as condenser. It goes to another chamber called as condenser. Condenser is the chamber where condensation takes place. The entire water gets converted into, the entire steam gets converted into liquid water, and then from this liquid water, it gets pumped back into the boiler. It gets pumped back into the boiler, the liquid water. And guys, this is the cycle that keeps on running. This cycle keeps on going in a thermal power plant, in a coal-based thermal plant. And why this process is considered to be so polluting? This is a highly polluting process. The reason is because we are burning coal. We are burning coal for this entire process, and that's why it is considered to be polluting. Otherwise, the water keeps running in a cyclical manner from boiler to the turbine to the condenser, and back to the boiler. It keeps on going like this, right? This is a simple working of a thermal power plant. This is how thermal or coal-based power plant works. You'll be surprised to know, guys, that between a coal-based power plant and a nuclear power plant, between a coal-based power plant and a nuclear power plant, there is literally no difference. There is no difference between a coal-based power plant and a nuclear power plant. The only difference is, in a coal-based power plant, the heat source is coal. In a nuclear power plant, the heat source is a nuclear reactor. That is the only difference. Between a coal-based power plant or a nuclear power plant, the only difference is the source of heat. In coal, we are burning the coal and that gives the heat to the boiler. In case of a nuclear power plant, we have got a nuclear reactor. This nuclear reactor provides the entire source. Nuclear reactor provides the entire source of heat. So you guys can see in this particular diagram, you can see the nuclear reactor mentioned here. The nuclear reactor is the place where the actual nuclear reaction takes place. This nuclear reaction produces heat, and you guys can notice the heat is moving out. Can you guys see? The arrow shows the heat is moving out of the reactor and going into the steam generator. This steam generator is nothing but the boiler. The steam generator is nothing but the boiler, right? And from this, the heat that goes out from the reactor into the steam generator, we get the superheated steam here. And the superheated steam, you guys can notice, it is going all the way to the turbine. The turbine is going to have the turbine fan, the turbine blades. They will start rotating, and as they rotate, you can see the generator here. The generator is going to power the electricity grid. Are you guys able to notice how simple it is? And then from the turbine, the used steam goes into the condenser. As you guys can see, the condenser is going to convert the steam into liquid water, and all this water goes back into the boiler or steam generator. Can you guys notice the working of a thermal power plant and a nuclear power plant is nearly the same? The only difference lies in the production of heat. In the thermal power plant, it is the burning of coal that produces heat. In a nuclear power plant, it is the nuclear reaction that produces heat. Tell me yes in the chat if you guys have been able to understand. Tell me yes in the chat if you have been able to understand up till here. Right? So the process of a nuclear power plant and a thermal power plant is nearly the same. The only difference is the source of heat. So guys, we don't have to look. So you must be, surprised to see such a big image or such a large image, but we don't have to study the image at all. We only have to study the reactor vessel. Because rest of the cycle is common. Rest of the cycle is completely common. We only have to study the reactor vessel. Rest of the cycle is completely common, guys. Only the reactor vessel needs to be studied. Baki sab ekdam puri tarah common hai. Got it, all of you? So this is what we have. So now let us see how the reactor vessel really functions. So we have to only see the working of the reactor, nothing else, because everything else is common for every power generation or power station. Okay. So let us talk about the reactor. So guys, when you talk about this pressurized heavy water reactor, actually this is what pressurized heavy water reactor is, not the entire diagram. The entire diagram is not pressurized heavy water reactor. Only this part is pressurized heavy water reactor. And when you notice the pressurized heavy water reactor, you can easily also notice the entire features here. You can see some of the features clearly. It has got a pressurizing system. This pressurizing system is applying pressure onto the reactor. You can see this is the reactor. The entire reaction happens here, right? The pressurizing system is simply there to apply pressure. And guys, this reactor basically have high pressure heavy water. So this reactor is completely filled. This reactor is completely filled with high pressure heavy water, right? This reactor is completely filled with high pressure heavy water. And guys, what is the boiling point of this heavy water? 900 degrees Celsius. 900 degrees Celsius is the boiling point of this particular water. Are you guys able to understand? So this is basically filled with high pressure heavy water. Now guys, it is already 9:27. I want to talk about the working of the nuclear reactor. So we'll talk about the working of the nuclear reactor tomorrow, right? Tomorrow when we meet, we'll discuss the working of not tomorrow, in the next class. Achha, next class will be after 1 week. Chalo, we'll finish the working of the nuclear reactor here itself. We'll finish the working of a nuclear reactor here itself. But there are few topics that I want to talk about, like moderator, right? All those things are there. So It will take some time. I don't know if we can finish it today. Guys, let's do one thing. Let's continue this part in the next class, right? Because in the next class, I will be able to give you some entire recap of whatever things we have covered, right? So I think it will be better, because if I finish, actually, why we are waiting for 1 week, I said this previously also, because we are expecting some more admissions, right? So we are waiting for students to enroll for these first 5 lectures, because these first 5 lectures were available for all the students. All students could join in, and then they can take admissions, and then from 18th we'll go in one complete sequence, right? We'll go in one complete sequence. No, for environment we are going to continue, because for environment our demo classes and all those things were already there on YouTube. So for environment we are not going to have a break. For environment we'll continue. It will not be having any break in between. Only for science we'll have a break, right? And that too for 1 week. And then again we'll be meeting on 18th, and then we'll finish the entire subject of science in one go. Okay. For environment we'll not have any such breaks. We'll have 6 classes a week for environment, right? Yesterday I could not take the environment class, mainly because it was Raksha Bandhan yesterday, so I couldn't take the class, but I'll compensate yesterday's class next Sunday. Okay. So that's how we'll be covering up the things. So what I'm going to do next time when we meet, please do remind me, those of you who are going to be there in the next class, remind me to talk about, to start from pressurized heavy water reactor. Although this particular image will remind me that at what level we have reached, although still I would expect you to remind me to start from pressurized heavy water reactor, and whatever is the background that is needed to understand to reach pressurized heavy water reactor, I'll explain that part in just 10-15 minutes of discussion. Okay. So guys, that is everything for today. And no, today will not have Sunday is usually going to be an off. Sagar, Sunday will be an off. Even for science, Sunday is going to be an off. I took science class today mainly because it would have helped the first 5 lectures in one go, and then every Sunday would be one off. And you also need time for self study. You also need time for writing answers. So that's why we have kept Sunday off. But 6 days a week we'll have the class. So yesterday we could not have the environment class. So today we'll not have environment class. Today, unfortunately, I have some work to attend. Next Sunday we'll have the environment class at the same time, 2 to 4, right? So that's how we'll finish everything else. All right, guys. So this is everything for today, and we'll be meeting, guys. For environment, we'll be meeting tomorrow anyway, right? And for science, I'll be seeing you guys on 18th. I hope all of you who have taken the demo classes, they would join, and we'll be able to have much better discussions in the class when we meet on 18th. All right. All the best, students. Thank you. Thank you, guys.